Okay, so for the homework, the next web work is due Monday at midnight. And so after today's class, you should be able to do most, if not all of that, or work on and get help for all that web work. So what we cover today pretty much covers that web work, due Monday at midnight, and then our next written assignment will be due Wednesday as normal. Okay? So what are we doing? We've looked at all these different applications of what? You know how fast something is changing at every moment? You want to know how much you have at every moment, right? And that was building our accumulation functions from rate functions, right? And then every application we did surface area and volume and area and work. It was always, we found an open form, right? An open form accumulation function, which means an integral, right? And while open form is great because it reflects the process and we're looking at the mechanics of it, accumulating little bits of change, we also, for those open forms, we also want to find closed form, right? Closed form allows us to crank out values of the accumulation rapidly, right? They're like easy to work, functions that are real easy to work with, can generate results. So we started last time talking about, and then we saw that in order to do that the fundamental theorem tells us that that's a matter of antiderivative, right? If you have a rate function, antiderivative of the rate function is going to be the key to a closed form accumulation function. So we're going to start learning these antiderivative techniques, which will allow us to write these accumulation functions in closed form. So we started talking about undoing the chain rule last time. So as we do as we learn these techniques, we don't want to learn a whole new set of techniques. What we want to think about is we have all these techniques for derivatives from Calc 1, and I'm pressing forward assuming that you know those, right? So you took a mastery exam, you learned the chain rule and the product rule and the power rule and the quotient rule and all the exponential and all the trig forms. You learned those derivatives. So rather than learning a whole new set of rules, we want to leverage those and know them well enough so that given a function, we can think, okay, what function, if we took the derivative of it using our derivative rules, would we get the one that I have, right? So it's like using all those derivative rules that we learned in Calc 1, but now it's like a step harder. You got to kind of think it in reverse, right? So what function? So I'm looking at a function here. It's a rate. I'm looking at a rate function. It's the derivative of some function. What function, if I took the derivative of it, would I get this rate of change function, right? That's our mindset through this whole unit, okay? That's our mindset. So the first kind of technique for these harder ones is undoing the chain rule, recognizing that your rate of change function came from the chain rule. So let's practice. So since we're going to be basing all of our antiderivatives on derivative, let's practice derivative by chain rule. So that's a good place to start here. So this is chain rule derivatives practice. So for the functions f, h, z, and capital B, I want you to find the derivative, right? This is finding the derivative. This is like Calc 1, like the mastery test. Okay? For h, your hint is you're going to make it look like f first. Make it look like something to a power first, and then do the same thing you did for f. Okay? So you're going to take 5-ish to 10-ish minutes. Hopefully not 10, but maybe 5 or a little more to work on these. All right? So time to blow the dust off your derivative rules. Or learn them quick if you never learned them. You don't remember. As always, you can consult each other, work together. Egan, tell me about the first one. What'd you say? I'm just going to write the first step. So yeah, it's perfect. You nailed it. So 8 plus x to the fourth to the fifth times, and then she multiplied the 4 and the 6 together. Questions? This one. Oh. Let's see. Let's try this. There we go. Okay. Next one. Let's see. Somebody else. I love your enthusiasm, Carolyn, but how about Kyle over here? Did you get the next one, Kyle?
Yeah. So you would make it x to the fifth minus ln x plus pi to the negative 2. You make that like in the numerator, and you make it negative to the negative 1 half.
Right. Negative. That's the negative 1/2 power. Okay, go for it.
So you switch the power to the top.
Right.
And then you make it negative 1 half times x to the fifth minus ln x plus pi to the negative half times 5x to the fourth minus 1 over x minus 2 pi to the negative third.
5x to the fourth minus 1 over x, and then derivative of pi to the minus 2. Derivative of pi to the minus 2. It's not x to the minus 2, right? It's pi to the minus 2. It's a constant. Goes away, plus 0, right? It's not. This is not the power rule, because the power rule would be like your independent variable to the minus 2. This is a number, right? This pi to the minus 2 is just 1 over pi squared. That's just some number. Derivative is 0. Okay, one more thing. You probably have it, but you just spoke too fast. Right? What else did we miss there? New power.
The power of the first part would be negative 1 half, or negative 2 3
How do you do? Good? All right. Let's see. Harrison. Next one. So 3. You got a 3 in there? Okay, what else? Okay. Times what? Jesus, just go ahead and answer. 15 over 4 x? X to the? 1/4. Agree? So if you have a question, stop us. Just stop us. All right, last one. Let's see here. Dustin.
Is it sex or SEC squared
Secant squared
times cos x?
of, right? This function. This is not multiplication. This is a function. This is cosine x is the argument of the tangent function. So secant squared of cos x.
Cos x times minus sine.
Right. Okay, any questions on those? Any questions? Okay, so notice the pattern. So what's the pattern in all of these, right? What's the pattern in all of these? Please.
For the z of x1, how do we get 15 over 4?
So it'd be, you're doing the power rule on 3x to the 5/4. So 5/4 times 3. See it? When you bring the 5/4 in front, 5/4 times 3 is 15/4. Other questions? Okay, so what's the pattern here, right? What's the pattern? We got this part of it. Whoa, that, right? And then we got this part. So for these, so when we've got these rate functions and they're a result of a chain rule derivative, we're on the lookout for this pattern, right? We're on the lookout for something like this pattern, and we're going to recover the original function. So first of all, most of the time, as a general rule, how many factors do we have in the chain rule? How many factors? 2, right? 2 things multiplied together. And then if we undo it, then how many factors will we have? 1. So which one disappears? First or second? Second is going to, so the second was the part of, that's the chain rule, right? We chain on the derivative of the argument of the first, right? So when we undo it, that's going to collapse back inside and go away. And then we'll have just the one factor. So this is the thinking we have. We're going to have a function the rate function that looks like the ones on the right, and we have to recover the one on the left. Okay, so let me give you let's do an overview of what that's like. But again, it's all our thinking the whole time is, okay, this is the result of the chain rule. What derivative, when I do the chain rule on it, do I get this? Right? What function, if I take its derivative, do I get this as the chain rule? So we want to really know the chain rule well. The better you know the chain rule, the easier this will be. Last chance for questions. Okay. So if you have g of f of x, like all the ones we just did, what's the derivative? How would you generalize the derivative? Good, g prime fx times f prime x. That's what we did on all of them, right? So antiderivative will be something like this. We'll start with this, g prime fx times fx, to recover g of f of x. So what are we going to focus on? So we've identified that we have a chain rule derivative. Now, where are we going to place our focus in order to recover the original function? Where are we going to focus? On exhibit A or exhibit B if we want to recover g of f of x? Exhibit A or exhibit B will have the information to recover. You should be thinking A. Look, exhibit B, that's what's going to go away, first of all, but it has no information about g. See that? It has no information about the function g. This has everything we need, right? It's got information about g and f in order to recover g of f. So the first thing is when we come to these, we're going to identify which is g prime f of x. So we're going to focus on that, right? So we're going to focus on g prime f to recover g of f. So what will the approach be? Okay, so we're going to write. So what will we do? So what's the only difference between g prime f and g of f? There's only really one difference. Yeah, so we've got the derivative of g. So we're going to identify what that exterior function is. That's g prime, and take the antiderivative of it, and leave the interior as it is. And that's almost all of it. That's almost the whole deal. We might have a little mess to clean up with a factor. Okay, but this is it. If we can identify the g prime f, then we're going to identify what the exterior function g prime is, take the antiderivative, and we're almost done. We're almost done. Okay, so that's just what I wrote in the last. So let's do an example here. So here's one. X cubed times 8 plus x to the 4th to the 5th. So first of all, we ask the question, does it qualify for undoing the chain rule? So what's the qualifying feature? The qualifying feature is that we have this right here. We have a match here, right? So the argument in this composite function, its derivative is the other part, right? So that's how we know that we can use undoing the chain rule. So do we have that here? All right, what is our g prime of f? Exhibit A or exhibit B? B, right? So B. So now, if we can do undoing the chain rule, that means that what? This is like essentially the derivative of what's inside. Is it? Yeah, it's just off by 4, right? And that's no problem. We can handle factors, no problem. So yeah, so this is the right power. It's x to the third versus this x to the fourth. And this is what we're going to focus on. So we're going to think of this like g prime f prime as the result of the chain rule derivative, and we're going to recover g of f, and you guys have already identified that this right here, that's the g prime f. So what did we say? So we said if we got g prime of f and we want g of f, then what do we need to do? Antiderivative of the exterior function, right? So the a plus x to the fourth to the fifth, what's the exterior part of that? Something to the fifth, right? And so we're going to do the antiderivative of something to the fifth, and we're going to leave the interior as it is. And that's what we're going to call our first attempt at this, first attempt. So what is the antiderivative of something to the fifth? To the sixth, right? So it's the opposite of the power rule, right? So instead of lowering the power, we raise the power. But then if we have to the sixth, we're going to need 1/6. And then what do I do with it inside? Keep it the same. And we call this the first attempt. Okay, then what we're going to do is, actually, have that first attempt. Now what we want to do is we want to check it. How do we check it? Take the derivative, right? So now we're going to use the chain rule like the problems we just did on the previous screen. We're going to take the derivative, and if it's exactly the same as what we started with, we're done. But it might be off by a factor, and then we'll make a second attempt based on how it's off. So chain rule, right? So we're just, now we've got this problem, we're going to do the chain rule, take the derivative. Alexandria, can you do that for me? Let's take the derivative of this. Right? And then chain rule. How'd she do? That's the chain rule, that's right. So now we compare it. Is it exactly the same as what we started with? No. How is it different? We have an extra multiple of 4. So now we ask, okay, how do I revise my attempt so that when I take the derivative, the 4 won't be there? Times 1/4, right? So all we have to do is take the first attempt and include another factor of 1/4, and we'll have it. So it'll be 1/4 times 1/6. Okay, and if you need to check, if you want to check it again, that's perfectly fine. Go ahead and do the derivative again and check it. But we can. This is right. We can trust it, and then we can simplify it as. Okay, so say this is like from A to T. So we got the antiderivative, and now if we have an accumulation function, say from A to T, here's a notation that means, so remember from last time with the fundamental theorem, once you have the antiderivative, you're going to do it antiderivative evaluated at T minus the antiderivative evaluated at A. Remember that? F of x minus f of A. Okay, so here's notation to represent that. You can put now on the right side, you can put a bar with your limits like this, and that's what that means. That means plug T in, plug A in, and subtract. So then we're finishing out the fundamental theorem. So it would be T minus to the sixth. Okay, so that would be our closed form for this. So what I wrote here, the a and the t, is the same. It's kind of the same idea as if those weren't there, right? So whenever you see an integral where you don't have limits, okay, where you don't have limits, it's called an indefinite integral. It means the same thing as starting from any x value, starting from any value of the independent, which we call a, and then to our, our independent variable, in this case t. So oftentimes, since this is just a constant now, right? This is just a constant because it depends on only a, which is where we're starting the accumulation from. So what we can do is, since that's a constant, we can just, instead of writing that out every time on these indefinite integrals, we can just use, so this minus times this is the same as, say, plus c. So this whole thing with the minus, we can just say plus c instead of writing all that out. And so that plus c is accounting for every accumulation function, right? Starting at any value of a, right? So we could start at any value of a, and we know that we would have this minus this term. But as a shorthand for that, rather than write all that out, we can just write plus c, meaning all the possible constants you would get for all the possible starting values a. Does that make sense? So that's what we mean by, so we have the antiderivative, we say plus c. So this is the whole family of accumulation functions that have that as the rate of change with any starting point a, with any starting point a. So you'll use this in the web work, right? In the web work, they'll give you lots of these. Can you imagine that there's an a and a t there? They won't be there, but imagine there's an a and a t. And then you can just write plus c to mean this minus f of a part. Which again, this is the family of accumulation functions that have that rate of change starting from any value a, which is which we attribute to the plus c. Yeah.
Does the plus c make it a total accumulation function?
No, it's different. This is the minus fa, right? So f of t minus f of a is still net accumulation. So adding the c is just replacing this part of it. So it's still net accumulation. Yeah, good question. So this is not the same as the adding for the total accumulation. This is the minus f of a part. So it's still a net accumulation. All right, did that make sense? Okay, more examples. Here we go. Any questions on finding this antiderivative? All right, next one. Okay, how is this one different? What is it about it that makes it not look like chain rule? Yeah?
Sine fourth of x instead of like sine x to the fourth.
Okay, that's one part of it. Yep. So cosine x over so this is the same as sine x all to the fourth. That's good, but it still doesn't look like what we need it to look like. Why not? Yeah, I mean, what is chain rule is you get a product, right? And this is a fraction, but we can write any quotient as a product. So that's what we want to do first. Cosine x times what? Sine x to the negative 4. Now we're ready. Now it looks just like that. So now what's the first step? Determine which is g prime f and what's f prime. Verify that chain rule actually works because by this, right, that your derivative of your interior is the other factor. Verify that. And then once you verify that, then you're ready to go and start working on g of f. So what is g prime of f? Is it cosine or sine x to the minus 4th? Whoa. Sine x to the minus 4th. And do we have the right condition here? Is cosine the derivative of sine? Yeah. So we're good for undoing the chain rule. So Will, what do you think the first attempt is then? Okay, so it looks like you took the derivative.
Oh,
Okay, it was perfect, right? You took the derivative, that's perfect. But we're going to do the power rule the other way, right? So our new power is going to be, when we're doing antiderivative, the power rule is add 1, right? Add 1. So then what will we need in front? Negative or positive? Negative 1/3, right? Stop me if I lose you. Okay? Now we're going to check it. We're going to check it with the derivative. Let's do that. Megan, you do the derivative on this? So yeah, so so -3 multiplies down here, right? -3 times, you probably did that in your head, that's perfectly fine, of sine x to the times cosine x. Yeah, you said that before. Okay, which is exactly the same as the original function. Done, right? So the whole family of accumulation functions is so we could have a minus all this with the a in it, right? Or we just write plus c. Same thing, right? So it's that plus c is the same as minus that with a. And so we get what? All accumulation functions that have this as the rate starting from any x value a, right? Starting from any x value a, the net accumulation. Okay, questions? Do you follow? More practice. Here we go. Can I erase? Try it on your own. See what you can do. Again, did you make any progress on this? Tell me how you started. Tell me everything you did. Great start. Okay. Good. Nice. Yeah, so our focus is this. The g prime of f is the second one. Yep. Okay. So the question is, so what is our g prime, right? What's the exterior part of this? Good, something to the minus 1. And we need to take the antiderivative of something to the minus 1. Okay, all right, so this is good. I want to do this. So to the 0, and then we would need 1 over 0. Okay, so what's anything to the 0 is what? 1. So there went our function. It's gone. Function's gone. And then we have 1 over 0, and what's that? Undefined. Okay, so I love this because so if you try the power rule on this, you get awesome warnings, right? That something is wrong, right? We just lost our function because everything to 0 is 1, and then then the whole thing's undefined. It's like warning, warning, something's wrong here, something's different, right? So David wants to tell us.
You use the natural log.
All right, so this is the one case where the power rule doesn't work, right? So then you think, okay, what is it when I take the derivative of it, do I get it to the minus 1? Or natural log, right? Natural log was that one case. You take the derivative of the natural log of something, then you do the 1 over, or to the minus 1. Okay, so, but if you forget, it's giving you all this help, right? It's giving you all this help that something's wrong here. You got to remember that it's not going to be going to be that. It's not power rule. So this is the one case you don't use power rule instead. So David, tell me.
Negative 2/3 times the natural log of
Cool.
2 minus 9x plus c.
All right, I'm going to, if it's okay with you, I'm going to do 2 minus 9x, natural log of that. And then we have a 6 here, so we could just hold on to the 6 in that first attempt. So is that a fair first attempt at this? 6, just hold on to the 6, and then the antiderivative of something to the minus 1 is ln of that something. So now, check it. Derivative. What's the derivative of this right here? Aaron.
So it would be 1 over
1 over.
and then 2 minus 9x
Okay.
times 6 times negative 9.
How do you do? Is that the derivative? So we hold on to the 6, take 1 over that, and then times the derivative of the interior, which is negative 9. Nailed it. Is that exactly what we have?
No.
No. How's it different? We've got this extra negative 9. So how do we revise our attempt? So when we take the derivative, we won't have that factor of negative 9. So we've got this 6, yeah. So we're gonna divide by 9, right? So we're gonna 6. We're gonna also take negative 1/9 or divide by 9, right? And that's the negative 2/3 that you said. And then if we want all antiderivatives that have that rate function, what do we do? Plus c, which is, again, just to remind you, would be minus 2/3 minus negative 2/3 ln of 2 minus 9a. So that's what that plus c is. This thing right here, that's what the plus c is, according to the fundamental theorem. Questions on this example? Yes, sir.
Shouldn't the 2 minus 9x in our final answer be an absolute value?
Yes, thank you. All right, so great job. So this is defined for all real values except 2/9, right? So our domain here, our domain of the rate function is all values except 2/9. Do you see that? So we need the domain of the resulting antiderivative to be the same. But natural log is only defined if this is positive. So by putting absolute value around it, that makes the domain of the antiderivative the same as the domain of. So now we have the right domain of our antiderivative as compared to the original rate function. This is all real numbers except 2/9, because ln of 0 is undefined. But now we can put in anything else, and we'll always be putting a positive number into ln. So that's why you need absolute value. Extra credit. Good point. So, and watch this in web work, okay? You're going to have these in web work. Don't forget the absolute value bars on your natural log antiderivatives. Yeah? Yeah, it's always safe to do that, right? So some you don't need to, like this because of this expression, it's already automatically positive, but it will never hurt. Just always put them on. Yeah, just always include them. And why? This is a domain issue, right? So we need the domain of our accumulation function to be the same as the domain of the rate function. Okay. Lots of examples, lots of examples. Try this one. Megan.
Is it 1 over the natural log of our tangent?
Not quite. 1 over, like this. So if we were, so let's just take the derivative and see what we get. Okay, so that's the same as natural log of all to the minus 1, right? So is that the same as your answer? So if we took the derivative of that, we'd get minus 1 natural log tangent inverse to the minus 2 times 1 over, so now the derivative of this, which is 1 over tangent inverse x, times the derivative of that, double chain rule. So it's not, so it doesn't work. It doesn't work. There's way too more involved than what's going on there. So that's all right. But that's the thing. Like, give it a shot. Take the derivative, and then if your derivative is close, then you know you were close. If your derivative isn't close, then you know you're on the wrong track. Anyone else think they correct it here? All right, so let's look at the form. Let's look at the form here. So which is the f prime? So which is the f prime, right? So which one is the derivative of the other one? This is the f prime of x, right? Because it's the derivative of tan inverse x. So that means tan inverse s is f. So the question is, what is g? What is the exterior function for tan inverse of x? This is the tricky part. Yeah. To the power of 1. Oh, they got in the back too. To the power of 1. So when you do the power rule on something to the power of 1, Christian, did you finish it?
Then it would be tan inverse x and then squared.
So the g prime is just something to the first power, but you never write that. You just leave it as it is. But you have to imagine that the g prime is this thing, something to the first, and the antiderivative of something to the first is 1/2 that thing to the second. All right, check it. So take the derivative, 2 times 1/2 tangent inverse x to the first times 1 over 1 plus x squared, the derivative of tan inverse. Is it exactly the same as what we started with? Got it. So it's 1/2 tan inverse plus c, which means all net accumulation functions with that rate starting from any a, right? Starting from any a. Okay, so now you got lots of good background to work on both the written and the web work due Monday night.